So yesterday we have derived the conditions of Legendre transformations and the properties of the generalized thermodynamical potentials. And what we are going to do today, probably maybe the last parts of thermodynamics, I'm not sure that we'll finish today, maybe we'll somehow do it also next week. And we are going to talk about stability criteria. Stability criteria. Okay. Now, what is stability criteria and where this term is coming from? It's actually coming from mechanics. If you remember, usually in classical mechanics, or in analytical mechanics, if I have one-dimensional problem, and for this one-dimensional problem, I can define potential energy U of x. Right? The moment that I have U of x in one dimension, the problem is solved. I hope you all know this. For any one-dimensional problem in classical mechanics, the moment that I know what U of x, I can solve it exactly. Maybe I cannot solve the integral over there, but the solution is always known. So let's assume that I have some sort of potential that looks like this. Okay. So this is my potential. And I know that there is a condition that the force F equals to minus du to dx. What it means that if my system is located at some x1 over here, I should look on the derivative or on the slope of the function at this exact point. Okay, so if the slope is negative, du to the x is negative. Due to the minus sign over here, the force is going to be positive, and the particle will feel a force that will drag it to the right. Okay, if the particle is sitting in this position, call it x2, the slope is positive due to the minus sign over here. The force is going to be to the left. Okay. So we can imagine as if we have small ball over here. Okay. Small ball over here. It actually is driven by those forces, and it's going from left to right and from right to left, etc., etc., etc. Okay. So as if I have a slope and I have a roller coaster and I have a ball and it's just rolling on top of this roller coaster. Great. Now, stability is something that we deal when we look on the extremum of our potential. Okay. Now, if I place my small ball exactly at minimum of my potential energy, call it xm, okay, small m, the derivative of the potential at this point is 0. So there are absolutely no forces that acting on the particle when it's exactly at the lowest point, at the minimum point. Okay, great. So no forces. Stability means that if I'll drag my particle a little bit to the left or a little bit to the right, the system will act to return it to the original position. Right. So if I'm dragging the particle a little bit to the left, the force is to the right. If I'm dragging my particle a little bit to the right, the force is to the left. So I have always restoring forces, and the system is stable. Stable to what? To small fluctuations, right? It's in classical mechanics, the moment that I put the system in a specific position, specifically where there are no forces, it's going to stay there. In statistical physics or real normal system, we have always fluctuations. We have always small effects, noise, interactions that will try and drag the system a little bit to the left or a little bit to the right. So in order for the system to stay in equilibrium, okay, it has to be at a minimal point somewhere. Okay, so it's not enough. It has to be an extremum. It has to be a minimum. This is why, right? You remember we derived from the first and the second law of thermodynamics that the equilibrium state occurs when the energy of the system is minimal, right? We can have extremum points like over here, which are not stable, right? So, for example, if I put my ball in this maximal position over here at xm, what happens is if I drag my particle a little bit to the right, there are going to be forces that will drag the particle further away from this xm large. If I shift my particle a little bit to the left, there are going to be forces that will act on the particle and move it further away from its original point. So when I'm speaking about equilibrium, I'm also assuming that equilibrium has to be stable, right? Because what are the conditions for equilibrium? The conditions that if I leave the system at this state, okay, it will not go anywhere, right? This is what equilibrium, and we know that in equilibrium, the entropy is maximal, and the energy, as for this point, as for this picture over here, it's at minimum. Okay. Yes? Well, there it's not my problem, actually. There is nothing that I can do, I'm sorry. I can say that everything is recorded, and as I know this equipment over here, they will hear me in the recording. Sorry about that. Yes?
This is not any specific model, right? This is just a generalized
potential. A generalized potential, yes. A generalized potential. Generalized idea.
A generalized force.
Yep. Yeah. The same goes for our case, right? So we need stability criteria for our system or a general system at equilibrium. Because what we need to assume is that A, the system at some sort of minimum, right? It has to be there. Otherwise, there are going to be forces that will drag the system away. Okay. B, it's indeed minima, not just some extremal point. So that small fluctuations, okay, that are always present for any system, okay, where the temperature is not zero, there are always some small fluctuations, microscopical fluctuations and some macroscopical fluctuations, that those fluctuations won't drag away this point from the equilibrium. Right? Equilibrium is a stable state. So this is what we want to derive today, those stability criteria. Now, the first part of extremum is actually pretty simple, and we've seen what happens over there. Right? So we've seen that, for example, at equilibrium, the temperature is exactly the same everywhere in two systems. So what we have done, to remind you, so take my system and separate it into two different systems. Okay, so for example, this is going to be E1 and this is E2, and here I will have T1 and here I have T2, here I have S1, here I have S2. What we know that if those two different systems are in contact and in equilibrium, we have shown that T1 equals to T2. Okay. Now, I can extend this idea from two systems to three systems. For example, I will add an additional system. I will put everything in contact. I will wait. It will reach eventually an equilibrium. So we'll have E3 over here with T3 and S3. By extending the argument that we already used to show that T1 has to be equals to T2, also has to be equals to T3, and etc., etc., etc. What it means that if I'll construct huge system, okay, or I'll have general system that combine from many, many, many parts, okay, by using this argument, okay, so here I have T4, and here I have T6, and T7, and etc., etc., etc. By extending this argument, I can say, well, the temperature at every macroscopical part of my system has to be exactly the same. Okay. Now, it's not that just the temperature exactly the same everywhere, it's uniform. Actually, any generalized force has to be uniform across the system. Okay? So let's show it. And we use exactly the same idea as we used for T1 and T2. We will start with two systems. We'll see what happens if they are in equilibrium. Okay, so I have, again, E1 and T1 and S1. And let's assume that I also have V1, and I have mu1, and I have N1. So anything that I have are P1. So my system has a specific energy, it has temperature, it has entropy, volume, pressure, number of particles, chemical potential. If you have additional generalized forces, we can include them in this description. The same goes for E2 and T2 and S2 and V2 and mu2. What do we have also? N2 and P2. Okay. Now, we know that d E1 plus E2 equals to 0. Right, so the moment that we put the system, and the system is at equilibrium, so if there is some flow of energy from part 1 to part 2, okay, it has to be performed in such a way that the total energy of the system is not modified. Okay, stays constant. So we can say that dE1 plus dE2 equals to 0. What else we can say? Well, dV1 plus V2 is also 0. Okay, so the extensive variables are not modified because the total system is in equilibrium. Nothing happens. So the volume stays the same. The energy stays the same. What else stays the same? The temperature stays the same, right? ds1 plus s2 equals to 0, and dn1 plus n2 equals to 0. Extensive variables are exactly the same. There can be some exchange of those variables between system 1 and system 2, but in general, they stay exactly the same. Okay, so if we have this, let's focus on this equation over here. Right? We write dE1 plus dE2, and we know that it equals to 0. Okay. Now, let's use the expression for the differential of the energy for each system. So here we have P1 ds1 minus P1 dV1 plus mu1 dN1. Okay? So this is the expression for the differential of the energy of the left-hand side. Okay? Plus, we also have the same expression for dE2. It's going to be T2 ds2 minus P2 dV2 plus mu2 dN2. Now, there are some connections between the extensive variables, right? We have written this over here. So, since the differential of V1 plus V2 equals to 0, dV1 equals to minus dV2, and ds1 equals to minus ds2, and dN1 equals to minus dN2. Right, so let's plug everything inside into this form. So we have T1 minus T2 ds1. Okay, I replaced ds2 by minus ds1. We also have minus P1 minus P2 dV1. Okay. Also we have plus mu1 minus mu2 dN1. Yes?
But you said the temperature should be the same.
Oh. Let's assume that they are not. And you will see what happens. Okay? And you know that everything here equals to 0. The next statement is, oh, the temperatures should be the same. So look on this. So we have something multiplied by ds1, something multiplied by dv1, something multiplied by dn1 equals to 0. Now, there is no connection, okay? They're not connected to each other. They're free variables. ds1 is not exactly dependent on dv1 and dn1. They're completely independent of each other, okay? ds1 independent of dv1, independent on dn1 in general, and they're not restricted, okay? I can make ds1 as large or as small as I like. I can make dv1 as large or as small as I like, and I can make dn1 as large or as small as I like. Okay, it doesn't matter what the fluctuations do to the system. Maybe some energy goes from here to there, some fluctuations of the volume, some fluctuations of the number of particles. But in total, I know, so they are completely independent and not restricted generally. But I know no matter what happens, it always has to be 0. So since it's always have to be 0, what I obtain that everything that stands instead of ds1 and dv1 and dn1 has to be 0 as well. It's like vectors, right? When I have a sum of independent vectors, and this sum it's equals to 0. The only way that can happen when the coefficients of those vectors equals to 0. The same thing as I have over there. Right? So we have T1 equals to T2, and we have P1 equals to P2, and we have mu1 equals to mu2. You have some additional generalized forces. They're also going to be exactly the same. Okay. So what this condition means, okay? This means that in equilibrium, all the generalized forces across the system as the temperature are uniform. On average, right? Because we always measure average values. There's always some fluctuations because we have a macroscopical system. But on average, the pressure everywhere inside the system is exactly the same. On average, all the chemical potential is exactly the same. All the temperature is exactly the same. Now, what this means, when the forces are equal to each other, means that there are no flow, right? If I have a force, okay, if the force over here is larger than the force over there, eventually this force will win, and it will drag me towards there, right? Equilibrium is achieved when everything is equilibrated, and there is no way that I can push one particle systematically from here to there. Why? Because the forces are opposing to each other. This is what happens, right? All the forces are exactly the same. This means that in equilibrium, if all the forces are the same, there are no currents. So you're basically sitting or over here or over there. This is your minimum. Okay? No forces, no currents. This is what happens in equilibrium. Okay. Yes.
I wanted to ask, how do we know that the total entropy is conserved? Because
I close my system. I haven't let the adiabatic pose an adiabatic boundary constraints.
But what if we?
Otherwise, the system won't reach equilibrium.
But for example, we know that when we have a barrier with 1/2 of the container full of gas, and
no, this is not equilibrium. I'm saying the system at equilibrium. Of course, you can do something peculiar to your system. Okay, say, Stas, look on this. I'm looking on the system, and the entropy grows. Of course, because you prepare the system out of equilibrium, and as it reaches equilibrium, the entropy will grow. We're not talking about this situation at all. It's statics. I'm looking on the system. I'm saying this is an equilibrium system already. Everything is in equilibrium.
Oh, so this applies to quasi-static?
Not exactly. Any other questions? All right. Now, but you see what I tried to explain to you before is that we need to be at minimum, right? So those like conditions about the equivalence of, or that all the forces are exactly at the same position, okay, or exactly have the same values, can be applicable to this point and that point, because the only thing that I used, remember, that the differential equals to 0. I somehow need to use the fact that it's a minimum, right? But this is still not enough to say those are the stability criteria. Those are criteria that's saying that the system at equilibrium, it's in some sort of an extremum point, okay? So how we obtain the stability criteria, we need to use the fact that the system somehow is a minimum of energy, maximum of entropy, this kind of stuff. Okay, so what we're going to do now, we're going to develop the properties of those forces by saying we have to be at the minimum point. Now, how we are going to do this? Remember, we have developed this principle of maximal of entropy or minimal of energy, and this is what I want to use. I want to start with the maximal entropy principle in order to describe what and how the system is going to behave. To behave when I push it a little bit out of equilibrium. So I know that it's an equilibrium, there are no forces. Great. The idea is what happens if I push it a little bit to the right or a little bit to the left? I expect the system to go back to its original state. Okay? So again, let's play this game with two systems. Okay. So let's assume that I have a system. They're exactly the same. I put them together, they're exactly the same. So here, the entropy, which will depend on the energy, and it will depend on the volume, and it will depend on the number of particles. Okay, so this on the left-hand side, it equals exactly, because it's exactly the same system, to the entropy on the right-hand side, which have exactly the same energy, volume, and number of particles. Now, let's assume that some sort of fluctuation brought a little bit of the energy from the left-hand side to the right-hand side. Okay? So what I'm doing, again, I'm taking this ball over here and I'm pushing it a little bit to the right or a little bit to the left. Okay? That's the idea. So it's not exactly the equilibrium. I want to push the system outside of this small equilibrium. So remember, they are exactly equal to each other. Consider I replicated one system, brought it in contact to itself, and waited a while. So I have S, E plus delta E, V and M. Okay, so I allowed only some transformation from energy from here to there. So it's going to be minus. And here it's going to be E plus delta E, V and M. Okay. Now what I know, and I know that if something like that happens, there are the adiabatic boundary conditions, the system will return to its original state. I know this for sure, right? Because I assume that the system is in equilibrium, and this is equilibrium, and this is not equilibrium. Okay, so it's like the law of nature for me. When I do something like that, or I'm looking on a system that looks like this, I know that eventually, somehow, the system will go backwards. Okay? Now, keep it in mind, and let's see how exactly what it means on the properties of the function S as a function of the energy. So what we know about entropy and energy, this is the second law, right? So we know that entropy is a growing function of energy. This was an axiom that we call the second law of thermodynamics. And, well, I can say if it's a growing function, can look like this, right? So here I will have S, here I will have E. For this system, okay? Let's assume that this is how the entropy grows as a function of entropy. Is it right? Oh, it doesn't break anything, right? So the second law of thermodynamics states that it's a growing function. How exactly it's growing, we don't really know. Okay? So let's try and play this game of adding energy, subtracting energy, and how it affects this plot over here. Okay, so let's assume that this is the energy of the left-hand system before the multiplication on the left-hand side and the right-hand side. Okay. When we shift or we contribute the energy from left to right, the energy of the right-hand system is changing to E plus delta E, and the energy of the left-hand system changes to E to the minus delta E. Okay? Yes?
So we assume two systems are occupied.
Exactly the same. So everything else is exactly different. So I'm saying you took a system, you replicated it, and make them at contact. Okay? Everything is exactly the same. Yeah. Let's assume that's exactly the same. The argument is that there's exactly the same systems. Okay. So at this point, we know that, well, we can say that, well, we are modifying the volume and the number of particles, so let's forget about them for a second. So at this point, this is S of E, right? Now, at this point, this is S of E minus delta E. And at this point, this is S of E plus delta E. Okay. Now, let's plot a chord that connects those 2 points. A straight line that starts from here and goes over there. Okay? So this is my straight line. Why am I plotting this straight line? So if I have this straight line that connects SE and S minus delta E, I can go over here, right? And say, well, the total energy E, according to this straight line, okay, when it crosses it, it fits what value of the entropy? It's exactly in the middle between those two lines, right? Exactly. So this is SE plus delta E plus S of E divided by 2. So this is this value over here. Okay? This is this value over here. I'm looking at this and I'm saying, this is wrong. Why it's wrong? So it somehow do not abides to this law that I described to you. Okay? So what happens on the right-hand side? The right-hand side, I'm saying, I started from an equilibrium. There was a fluctuation that modified the separations of the energies of the left-hand side and the right-hand side. Okay? This is not an equilibrium. The system, due to the adiabatic constraints, will eventually go backwards to the equilibrium state.
But no, it cannot. Like the entropy is bigger.
Exactly. So if it goes backwards, it means that the A's entropy is higher than the entropy of this state. Okay? What is the entropy of this state? Is 2S of E, right? This is the entropy. Total entropy.
It's extensive and they have the same entropy.
You are right. What is the entropy over here? Is SE plus delta E plus S of E minus delta E. This is the total entropy. Now, from this plot, what we obtain, see, this SE plus delta E plus S of E minus delta E divided by 2 is larger or equals to SE. Or what we obtain is that the entropy of this state is larger than the entropy of that state. But this is equilibrium, so it can't be. Okay? If it was indeed the situation, the system would simply go to this state, right? There was some increase in entropy. Now, what will happen afterwards? Maybe I will move a little bit more from the energy from the left-hand side over here, and it will move away from the equilibrium and away from equilibrium. So if this is the case, or if this is the case, we are not at minimum. We're at maximum. Fluctuations drive me away from my stable state. Okay? So this property is wrong. What is the name of this function over here? Or what the property that I plotted? Concave, convex. So if you don't know, I will describe it to you. What is a concave and convex functions? So this function looks like this, okay? This is f of x, and this is x, okay? Called convex function. Convex function. Okay? In Hebrew, it's called kmura. Okay? If I have the other way around, so this is f of x, and this is x, and the growth goes like this, okay? This is a concave function. And it's called kau. All right? Now, the property that I described to you is a general property of a growing function, but I assumed that it's convex. In Hebrew, the names are always somehow, it's the opposite from what you think, right? So when I'm thinking about Kiora, it only reminds me Kiara, and I'm thinking, oh, it should be like that. But it's not. It's the other way around. So how will I remember the names? Whatever I think, it's always the opposite. Okay. For our case, what we do understand, we understand that if the entropy is a convex function of energy, it won't work, right? So this is what we proved. No matter what the energy is, in any position, or any function, any value of the energy, the entropy cannot be a convex function of the energy. Now, it is a global statement. It's not a local statement. It's a global statement. Right? So what I do have is the other way around. Right? So what should I have? Instead of having SE plus delta E plus SE minus delta E divided by 2, it's not greater than SE. It's smaller than SE. Right? So if I'll put the function the other way around, like this, okay, like this, okay, we will see that S of E will be higher than this S of E plus delta E plus S of E divided by 2, okay? Right. This is what I need. So the concave function property says that SE plus delta E plus S of E minus delta E always larger, it's always larger than S of E. Here I have divided by 2. Okay, so let's try and make something out of it. Right? So we have S of E plus delta E plus or minus 2S of E plus S of E minus delta E larger than 0. Fine. Now,
Why is it still larger?
it's smaller, right? Smaller. My fault. So it's larger in the convex part, and we're talking about concave. This guy. So it's smaller. Thank you. All right. So this is concave function of energy. Entropy is a concave function of energy. Local, it's a global property. Now, we play the following game. I want to obtain some local property. So we have SE plus delta E minus S of E minus S of E minus S of E minus delta E. Smaller than 0. Now we take these guys and we divide them, everything, by delta E squared. Delta E squared. Okay. So what we obtain? We obtain that we have S of E plus delta E minus S of E divided by delta E minus S of E minus S of E minus delta E divided by delta E, and all of this divided by delta E. And we know that it is smaller than 0. And then I take the limit, delta E goes to 0. Okay. So the general property of concavity of the function leads to this expression. It's still general for any delta E. I'm taking delta E to 0. And what do I obtain? What is this? Derivative. Minus another derivative divided by delta E. So it is a second derivative, right? A second. So d squared S to d E squared is smaller than 0. So this is the maximal property, okay? This is the maximum property. It comes through the fact that no matter what your system is, if you want your system to be able to reach equilibrium, the entropy has to be a concave function of the energy. Great. What will happen if I'll do it the other way around? So if the entropy is a concave function of the energy. Now, I'll take the same plot. And I plot E as a function of S. Okay? Remember, entropy, concave function of energy. This is entropy. What it means that energy is a convex function of the energy. Just flip it around, okay? So if you had this guy, okay, you flip the axis and you're getting that guy. That's it, okay? So energy as a function of entropy always have to be like that, right? And you can think about the same argument as I used. I took two systems, I look on the energies, I modify now a little bit of entropy. A little bit of entropy goes from the left-hand side to the right-hand side. What will happen? Because in equilibrium, energy is at its minimum, the energy has to grow. So the same argument applies, right? So any chord, this is a convex function, convex. Any chord that I draw on top of this function has to be above it, right? This is the property of convexity. You plot a chord, a straight line, it lies above the function. This is convex over here. For concave, you plot a chord, it's always going to be below the function. Okay? So if entropy is concave, energy is convex. Energy is a convex function of entropy. Energy, is a convex function of entropy.
Because when entropy is at
Because
max, so
in energy is
it's
at minimum.
minimum.
Exactly.
Okay.
Okay? This is the claim. Now, as over here, I obtained this guy. Okay. If I repeat my steps for energy as a function of entropy, okay, over here, right, what do I get? The opposite sign, right? So if it's convex, we'll get that d squared e to ds squared, it is smaller than 0. Well, thank you. Larger than 0. Okay. How do I do it? You repeat those steps every point, every time you have s, you write e. Every time you have e, you write s, and you change the sign from smaller to larger. Okay. Great. So we obtained 2 stability criteria. Okay. Let's write them down. So what we obtained that d squared s to d e squared is smaller than 0. What's more important is d squared e to ds squared is larger than 0. Now, so what we've done, we've used the maximal property of the entropy, and then we used the minimal property of the energy. The only thing that was important that we used extensive variable that was going from one system to another, right? So we had E, S, V, N, and we had E, S, V, N, okay? We made a fluctuation, or we assumed that there was a fluctuation. And the system now had E of S minus delta S, V, N, and here we had E of S plus delta S, V, and N. So it's the minimal property of energy and some extensive properties of entropy and energy itself. Now, what will happen if instead of modifying the entropy, I will modify the volume, V plus delta. Here I have S and V minus delta V. Okay. The whole argument repeats itself, right? I will continue the whole argument. I say, well, I draw a function, I will plot the chord. The energy is at its minima. Oh, it's its minima. It's going to be a convex function. It's going to be a convex function. The second order derivative with respect to the same extensive variable that I modified has to be larger than 0, right? So d squared e to d squared larger than 0. And what if I want to modify the volume? What if I modify the number of particles? If I modify the number of particles, I will get that d squared e to dn squared is also larger than 0. This whole argument of minimal energy, convex property, and second order derivative repeats itself no matter what is the extensive variable that I'm modifying. Providing the generalized variable, it has to be extensive. I will modify it. I will say, oh, that's a fluctuation. The system has to get back. The energy here is minimal. Means the function is convex. The function is convex. The second order derivative is greater than 0. Those are the real stability criteria. Now, why those are the real stability criteria? Remember, we already found that at minimum, there is something happens to the forces. Forces at any point, the generalized forces are homogeneous. Now, those equations tells us, well, how the forces are modified if I'm modifying the extensive variables, right? Because what are those second order derivatives? It's very, very nice that we have second order derivatives, but I don't really understand them. I want to describe those stability criteria in terms of forces. I know that dE, dE, it is dds minus pdv plus mu dn. This is the general equation that we obtained from the first law of thermodynamics. In general, T ds ds plus d e dv plus d e dn. Right? If I know that my energy is a function of S, V, and N, this is how the full, this is how the differential looks like. So P equals to ds minus P equals to dE to dV. Mu equals to dE to dN. We've already seen it several times. So if I have now d squared E to ds squared larger than 0, it is d to ds of dE to ds larger than 0, and I obtain that d, instead of d to ds, I'm substituting t, so dt to ds larger than 0. Okay. So at minimum or at equilibrium, forces are exactly the same, but we know, oh, how temperature is modified if I'm somehow modifying the entropy of the system. I'm going from one equilibrium state to another, okay? Or I have fluctuations. The temperature has to grow as a function of entropy. Now, I do exactly the same for dE to dV because I know that the second order derivative is positive. D squared E to dV squared larger than 0. I obtain that minus dP to dV larger than 0. Okay. And I also can do this for the third guy because my stability criteria, d squared NE to dN squared larger than 0, d squared E to dN squared larger than 0, means that d mu to dN larger than 0. These are stability criteria. The uniform way how the uniform distribution of the forces inside the system, it's enough to say we're at extremum. How these forces behave as a function of their conjugated variables. Notice that T is conjugated to S according to the Legendre transform. Right? When we went from one thermodynamical potential to other, we switched. We can switch T and S. We can switch P and D. We can switch mu and N. The stability criteria tells us, well, yeah, you can switch them in order to work with Gibbs or Helmholtz. Doesn't really matter, but in order for your system to be at equilibrium, those conditions has to be always satisfied. Right? Always, for any system that it reaches equilibrium, this has to be satisfied. So at this point, we reached the verdict, right? The verdict is, if you look on the equilibrium, forces are equal everywhere inside the system, okay? And if the system is growing or we increase the entropy, the temperature is growing. The other way around for the pressure, always a peculiar one because of the minus over here and the minus over there. But the chemical potential is also growing as a function of it. Okay. If it's not satisfied, your system won't reach equilibrium. Okay. Any questions about those equations over here? Yes.
I wanted to ask, is this equivalent to what we said last week, that the entropy at equilibrium must be maximal, and assuming entropy is constant, then at equilibrium the energy must be minimal?
So yeah, this is the outcome of exactly those expressions. Yes.
But isn't this like completely equivalent, not just an outcome?
No. So those guys and those forms are smaller. It's a smaller or less stronger statement, right? Because the stronger statement is the convex and concave property. Okay, this is an outcome.
Yes, but minimality.
Minimality with respect to what? You remember? To unconstrained values inside the system. This is something different. We modify the generalized variables. Right? So if you remember, what I said is that we have an internal separation, a membrane that's moving from one part to another. So unconstrained internal variables. The volume was kept constant. This is something different. What happens to your system if the volume is modified? Right? So it's a different statement. It's an outcome of this maximality principle. That's different. Yes.
What about ice?
What about ice?
Yeah, ice and water.
Mm-hmm. So what happens over there?
Well, if you ever froze a bottle of water,
Yes.
the ice expands.
The ice.
Not contracts.
Right.
More pressure built up than the volume.
So you have to go to a different phase. But what this says that, and this is a great question. So what this states, those expressions, they tell us a little bit. They tell us how the system, if I modify it a little bit, how the system behaves. Okay. So if everything is continuous, those equations have to be satisfied. But you described for us ice, right? So the water changes something. The whole behavior is completely different when I'm going from one state, I will call it phase, the liquid phase, to a solid phase. So this solidification changes something abruptly to the system. And when the system is modified, right, it's not a small modification. It's not a continuum transformation from one state to another, right? Those guys are satisfied as long as everything is like normal. I push a little the system to one side, goes slowly to that side. I push the system slowly to another side, goes slowly to the other side. So if everything, all those thermodynamical description is continuous, this is satisfied. Sometimes there are abrupt changes. They're called phase transformations. And this is what we are going to describe now. Transitions. And when phase transition occurs, something can happen. Okay? But as long as I'm in one phase and it's in equilibrium and I'm not doing anything funny, okay, the stability criteria have to be exactly as I put them. Okay? So it does not apply to what happened at phase transition, but it applies to water and then it applies to ice. Okay, but it does not apply to the transition from ice to water. Okay. Any other questions? All right. So we're going to phase transitions. And why phase transition? How phase transitions? And what exactly is phase transition? So I forgot to bring my laptop. Otherwise, I would show you a couple of movies of phase transitions. We will do it next week. So you'll have to watch me describing things. So if I'll take a kettle, and let's assume that this is my kettle, okay? It's a very primitive kettle. But it's out of glass, and it's filled with water. And we'll put ice, not ice. I'll start to heat it up by making a fire under it. Okay. So what will happen? So let's assume that the water it's at room temperature. Okay, so around 20 degrees Celsius. And little by little, some heat from the fire is transferred into the system. And the heat of the water, or the temperature of the water, starts to rise up. Right? I put a thermometer over here and seeing 22 degrees of Celsius, 27, 30, 60. And at some point, something interesting starts to happen that's related to your question. What starts to happen? So as I look at the bottom of my kettle, and it's a glassy kettle, so I can look on what happens inside, I will start to see a formation of small bubbles, okay, at the contact between the water and the metallic plate, which is the bottom part of my kettle. And not that those bubbles are forming, they are pretty small. Not that they are just forming at the bottom of my kettle, they start to rise up everywhere inside my water. Okay. Now, what those bubbles are, okay, so it's not that something happens to my metallic plate. It's not part of my metallic plate that starts to evaporate up, right? It's basically the same water that was over here transformed from the liquid state, as it was, to a vapor. Okay? And those bubbles are bubbles of vapor that now, due to the pressure inside the water, are going up. Okay? By the way, this heating procedure, etc., won't really work at space, but it's a different issue. So, as time goes, what will happen? So, anybody see a kettle at home when where you're preparing coffee or tea? So, what's the next stage? The bubbles are it's fine, but what happens to the bubbles? The bubbles grow. As I heat my temperature, those bubbles are not small enough. They are actually, well, I'm very, very close to the boiling temperature. Everything becomes some sort of a bubble, okay? Bubbles are very big, okay? And they're pretty aggressive, so this whole water rumbles and rumbles and rumbles. Now, those are two different phases. So this is vapor. And this vapor is surrounded by water, okay? The transition that happens is pretty much abrupt, right? So if you look microscopically, you can never really see anything microscopically, but when you look macroscopically, some portion of your water suddenly, and almost like that, in a contact with this metallic plate, transformed from a flowing material to air, right? That's what happened. And this transformation fascinated physicists, chemists, etc., etc. Why? Because look on all our assumptions in thermodynamics. Okay? In thermodynamics, everything is continuous. We have continuous functions. We shift the energy. We go from one state to another. everything flows continuously from one equilibrium state to another equilibrium state. But here you have a very simple example. The same goes for the transition from water to ice, from metallic, ferromagnetic, paramagnetic, superconducting, regular conducting, many physical examples where the transition, you had one single behavior, and like that you have another. So water is very different from vapor. It's a very different, it has very different properties, but it happens extremely fast, okay? And you cannot assume, well, no, it's I just somehow continuously pushed my system from one state to another. Something happened across the way. Now, how it's set, so those are phase transitions. We have liquids, we have vapors, we have solids. How the transitions between different phases, we have paramagnets and ferromagnets, we have different other conditions, flows and non-flows, how the transitions between different states occur. So you have learned in thermodynamics a bunch of things that I won't repeat about Carnot engines and etc. etc. So what you can do to a system to drive it from one equilibrium to another, right? We have some properties about what happens. But all those transformations were always continuous. What happens over here, right? So this is what I want to describe to you, or start to describe to you, in the next 25 minutes. We are going to talk about phase transitions and how we describe them in thermodynamics. All right. So first of all, remember that I told you about the assumption. The assumption that everything is modified in a continuous fashion from one place to another. Now, remember that, so basically, if I have a differential, differential describes a continuous function that can be, that it's for the mathematicians usually of C2 type, right? But I have a differential. And if I have differential, I have the function, and the function, nothing bad happens to it. So we can take an expression that have a bunch of differentials in it and build a function out of those differential equations. So what we choose to start with is this Gibbs-Duhem equation. Why? Because I want something that connects forces, my generalized forces, and not generalized variables. Because as in this system, right, I want to look on it without changing its generalized variables. I don't want to increase its volume. I don't want to increase the number of particles. I don't want even to increase maybe the entropy, but it's hard to say because I'm heating it up. Okay, so I don't want to operate. I don't want to operate on with the extensive variables. I want to operate with the intensive variables, because I know that they are pretty homogeneous around along the system. Now, the connection between the different intensive variables is provided by the Gibbs-Duhem equation. This is why we derived it. So there were two purposes. One, to say to you, well, Gibbs is pretty simple. Gibbs thermodynamic potential is just mu multiplied by n. But there was another purpose. So remember, it was 0 equals to minus s dt plus v dp minus n d mu. This was the Gibbs-Duhem equation. Actually, I wrote it down plus and minus over here. Minus, this is plus. Okay. This is the Gibbs-Duhem equation. So I can write it down. Let's look on how the chemical potential behaves as a function of temperature and volume. Okay, so I have d mu equals to dt s, minus s, and plus v dp. So those are small s and small v.
Diane.
So yes, so S divided by N, it is small s, and the volume divided by N is V. So you can say it is an entropy per particle, and it's a volume per particle. So this is my equation. And the assumption that everything is continuous, right? At every point. Now, this means that I can describe my chemical potential as a function of some control parameters, which I call generalized forces, which is the temperature and the pressure. Okay, so I can plot mu as a function of temperature and as a function of pressure. Okay. And it's going to be some function, right? The only thing that I know that it's a continuum function, so I can plot here a two-dimensional manifold which describes the behavior of mu as a function of T and P. There is an assumption about, well, continuity. Something happens, oh, it's always continuous. But nothing that I've told you so far. So mu is continuous, right? I push the system from one state to another. Okay, mu shifts a little bit. I push the system from one equilibrium state to another equilibrium state. Mu is modified a little bit. Great. Nobody told you anything about the derivatives of mu, right? So that could potentially exist crossing lines, okay, where the behavior somehow changes. So everything is continuous, but there is one function over here, and there's going to be another function over there. So think about it. I have this manifold and I have another manifold, right? And there is a crossing line between them. So each point on this manifold is the equilibrium state of my system. And I can continuously drive my system by modifying the temperature, heating it up, or applying pressure on the system from one state to another. I modify my pressure, something changes. I modify my temperature, something changes. Everything occurs continuously. I heat the water a little bit, the water transforms into water with some different parameters, which are my forces, my temperature, my pressure, until at some point I cross a line. Okay? There are always lines that you should not cross in life. So if you want to stay water, don't cross this line. Right? Don't heat the water too much. If you heat it too much, it's going to be vapor. So in the assumptions of thermodynamics, we can say, yes, we can continuously modify everything for our system from one state to another. But it doesn't mean that some properties won't attain a non-analytical form. Okay? So mu is analytically, or I would say continuously, is modified from one state to another. Okay? But it doesn't say that the derivatives of mu or other properties are not expecting jumps. Okay? So what we expect that there is a crossing line. There is a crossing line. Since this is a two-dimensional object, this is a two-dimensional object, this crossing line that separates phase A from phase B, okay, it's a one-dimensional object, right? So you have two-dimensional manifold, they're crossing each other somehow. So as a function of P and T, there are going to be a separatrix, so separation line that separates one state or one phase from another.
This is the unanalytic place to be.
Exactly. So if I want to describe this line, okay, if I want to describe it, it's somehow described by P and T. I don't really need mu, okay? It depends on the values of P and depends on the values of T. So here I would have phase A, and here I would have phase B, okay? And there is a connection between P and T, okay? If P and T sets over here, I'm in phase A. I'm in a liquid state. If I'm P and T in places me somewhere over here, I'm in a solid state or vapor state. Okay. Now, what happens? What happens over here? So mu is continuous, right? Mu is continuous, but its derivatives don't have to be continuous. So look on d mu again. Let's write it down. So d mu equals to minus s dt plus d dp. We control temperature and we control pressure. Temperature, we can add more heat to the system. We can pump out some heat of the system, so we control the temperature. Pressure, we can also control the pressure. We can apply external force, external pressure, okay, to increase it, or we maybe decrease the external pressure. Now, what happens? So mu is continuous. Its derivatives, the derivatives are discontinuous. So what are derivatives? So d mu to dt equals to minus s. And d mu to dp equals to the volume per particle, okay? So small s and small v. So this is volume per particle, and this is entropy per particle. The function is continuous, but the derivatives are discontinuous. What I mean, so in one point, I will have entropy S. I will cross to another phase, the entropy will jump, right? So there is a discontinuous transition, not in intensive variables, but in extensive variables. I have one specific volume per particle. What I mean by particle, if I'm looking on one single molecule, it jiggles around somehow, okay? Now, after it jiggles around, so it's in water, but it cannot jiggle too much because it will have many other particles, many other molecules around it, so it constantly bounces in them. So the volume per particle is actually small. Something happens because the system is heated up. I increase the temperature, and suddenly it goes into the vapor state. In vapor state, oh, I don't have nearby molecules. I can jiggle much more. Now, this happens not for one single molecule. It happens for many, many number of molecules. And the volume per particle suddenly grows from bouncing around to, oh, I have a lot of space. You all left, and I'm alone that left in this classroom, and I'm wandering around it. Okay? This is the transition. Entropy. Well, we don't really know by now what entropy is. Okay? It's related to heat, etc., etc. But what we will learn later, that entropy is the order of the system. The system was maybe a little bit more ordered, and now there are many, many, many other states that I can occupy. You all left. I'm here alone. I can sit over here and over there and over there and over there. And my entropy also jumped. And this happens abruptly and very, very, very fast. So those are the phase transitions. And since I'm using intensive variables, I observe that extensive variables are jumping. Okay? This happens in a fascinating way. Yes?
No, I just wanted to say that you have more degrees of freedom.
Not exactly, no. No, no, no. I don't have more degrees of freedom. That's exactly the point. The system, I bound it, nothing really happened. Okay? You don't have any degrees. So you cool in a bottle of water and it becomes ice. There are no more degrees of freedom.
But when you have a lot of molecules, it means you have more interaction and you cannot move as well as, like...
You have constraints. And those constraints, they are saying, let's assume that I have two particles, okay? They can go freely as they like. Suddenly system freezes. What I freezes? So the systems are much more feeling each other much more. So those particles now, instead of doing something like that, they're doing something like this. Okay? So the degree of freedom I haven't took it out. It's frozen. Okay? I have to satisfy, for example, that the distance between those two particles is constant. Okay? That's what happens. Okay, so how to determine? Question? Yes. Energy, it's in our class. Energy is always extensive. Always.
So if empty variables can change in phase position,
Yeah, it will jump. It will jump. Okay. You can release energy. So, for example, you have frozen. So 1 degree of freedom is frozen. Okay. You releases this frozen bond, and it goes usually into kinetic energy. And again, it's in a jump way. Okay, so last 10 minutes. How to find the phase separation line. Okay. And it's called the Clausius-Clapeyron equation, and we will derive it in a second. Very simple, very intuitive. So let's assume that I have a phase space defined by, or a block defined by the pressure and the temperature. And I know that there is phase separation line that lies somehow inside it. Okay. So I know, let's take a specific point, this point. Okay. Now, according to this plot, the chemical potential is exactly the same if I am looking on this line. So this line over here is this line over there. Okay. So I know that chemical potential have to shift continuously from one point to another, even on this phase separation line. So if I'm approaching this point from over here, or from over here, so this is phase A, this is phase B, and I'm approaching this point, what do I know? I know that eventually, if here I would have mu A as a function of T and P, and here I have mu B as a function of T and P, exactly at this point, mu A of T and P equals to mu B of T and P. Okay. Great. Oh, so this is our assumptions that the intensive properties are continuous. Okay. But it's not enough. I would say, all right, now we would move, because we want to find this phase separation line, we would move along this line on the left or on the right hand side of the separation line, and on the left hand side of the separation line. So what I performed over here, I have d mu b T and P. I shifted my point from this position into this position. And the chemical potential of phase B is modified by d mu b Tp. Okay, but the same I have done in phase A, right? I've shifted my point on the separation line from this point to that point, right? And my chemical potential shifted from by d mu A T and P. Okay, now because I'm moving along this line, I know that those two differentials have to equal to each other. Why? Because I moved along the line. It doesn't really matter I'm moving over here or moving over there. The continuity property of the chemical potential has to say, well, they've both been modified by exactly the same amount. That's equal to that. All right. Now, what this guy is equals to, what is the Duhem equation? So we know that this is minus S B dt plus V B dP. And this guy is minus S A dt plus V A dt. And they're equal to each other. Okay.
Isn't it VA ATP?
VA, oh, thanks. Two intensive parameters. Variables. Okay, so what do we have? We have the following equation. Let's make it this way. So we have minus SA dt plus SB dt equals to VB dt minus VA dt. So VB minus VA dt, and here we have SB minus SA dt. And out of this, as a very good physicist, we make an ordinary differential equation. We just divide by VB and we divide by dt. It's not different, okay? We obtain that dP to dt, and a division of two differentials for any physicist, that's of course a derivative, okay? And we obtain that this is SB minus SA divided by VB minus VA. So this is the differential equation that defines the slope of the phase transition line. It's called Clausius-Clapeyron equation. Now, in order for this to work, say, well, it's reasonable when there is indeed jumps in entropy and there is indeed jumps in volume. But are there phase transitions where volume do not jump? Okay. Or how this equation is generalized and what actually happens and how we find this phase transition. So it's like, well, it's great, but you need to know somehow about those values. Somebody have to provide it to you. How do we find them? Right? How exactly to obtain SB and SA and VB and VA? I don't really want to operate at all with entropies. Right? So what I do with this equation, how I actually apply it, well, it's very easy if somebody will tell you, oh, Stas, this is the entropy was 3, here the entropy was 2, the volume was 7, and here the volume was 6. Yes. And then I'll obtain a straight line. But how it actually works, and when it stops to work, can I have phase transitions when the volume is not jumping? The answer to those questions, maybe I will give you next week. Thank you all. לא, אני אומר שהמשתנים האינטנסיביים הם רציפים לגמרי. כשאני מסתכל על המערכת בשיווי משקל, הם צריכים להיות הומוגניים בכל המערכת. אוקיי, תחשוב על זה בצורה כזאת. נניח, לקחתי מערכת, סגרתי אותה, חיממתי אותה, ואני שומר על אותו חום, פה יש מים,